Welcome to this explainer. Today, we're demystifying something super cool, how analytic geometry acts as the essential translator between our human intuition about physical space and the complex math that actually powers machine learning. If you've ever wondered how a computer fundamentally understands the relationships between abstract pieces of data, you are in the exact right place. Think about it for a second. You and I, we instantly know a dog is similar to a wolf. But to a machine, they're just a random jumble of pixels. So how do we bridge that gap? Well, let's dive right in and find out.
You know, when machines look at the world, they don't see images or texts or your user profile. They just see vectors, lists of numbers. For instance, to an algorithm, a user isn't a complex person. They're just a vector representing age, total clicks, and maybe average watch time, which instantly begs the question, how on earth do algorithms calculate if two vectors are actually similar? How does Spotify or Netflix know your preferences are close to someone else's? To answer that, we really need to build a firm bridge between abstract algebra and physical geometry.
Here's how we're going to break this all down today. First, we'll look at similarity in machine learning. Then, inner products, which is basically our engine. After that, we'll tackle measuring lengths and distances, move on to angles and orthogonal vectors, and finally, wrap up with the power of projections.
All right, let's kick things off with Section 1, Similarity in Machine Learning.
So the whole point of a lot of machine learning algorithms is pretty straightforward, right? Predict similar outputs for similar objects in the real world. But to make formal, mathematically rigorous statements about that similarity, we have to introduce some specific operations. We need a function that can ingest two abstract data vectors and spit out a single, solid numerical score. Without that exact number, a computer literally cannot group a picture of a cat with another picture of a cat. That one number is what translates a vague, fuzzy concept into a definitive rule telling the machine, yep, these two data points are highly related, or nope, completely different.
Which brings us to Section 2, Inner Products. This is the core engine of our math.
We call this mathematical engine an inner product. Simply put, an inner product is an operation that takes two vectors as input and returns that single numerical value representing their similarity. But it does something profoundly important here. It fundamentally induces the geometry of the space itself. Think about that for a second. Before we apply an inner product, vectors are just meaningless lists of numbers floating in a void. They have no concept of space, shape, or scale. The moment we introduce the inner product, boom, it breathes physical space into them. It creates the very fabric of the geometry our algorithms are going to navigate.
Now check this out. The inner product isn't just one single fixed formula. The standard dot product you might remember from high school math is just one type of inner product. But if we swap out that standard dot product for a custom inner product, the rules of our geometry completely change. Let's look at the math here. If you take the exact same vector with coordinates 1 and 1, its length using the traditional dot product is the square root of 2. But under a different inner product, its length evaluates to exactly 1. Let that sink in. The very same vector is actually measured as shorter just because we changed the engine we used to measure it. The data didn't change at all, but the universe it lives in absolutely did.
Let's keep building on this with Section 3, measuring lengths and distances.
So how exactly do we find the length of just a single vector? Simple. By taking the square root of the inner product of a vector with itself, we get its length. Take a close look at the equation and that square root symbol right there. This is how we compute the very familiar Euclidean distance, also known as the L2 norm. And this simple operation is the crucial anchor that ties all our abstract, multidimensional algebra back into the physical intuition of space we actually experience every day. It's like finding the physical length of the side of a triangle. It gives our algorithms a tangible ruler to measure just how big a single piece of data really is.
Okay, but what about the distance between two completely distinct vectors? To formally define this, we use what mathematicians call a metric. And for any measurement to truly function as a distance metric, it strictly must meet two conditions. First, it's got to be positive definite, meaning a distance is always 0 or greater, and it's only exactly 0 if the two vectors are identical. Second, it has to be symmetric. Think of it like this. The physical distance from New York to London is the exact same as London to New York, right? Well, our mathematical metric must behave the exact same way. The distance from data point x to data point y absolutely must equal the distance from y back to x.
Moving right along to Section 4, Angles and Orthogonal Vectors.
So we've built our ruler for distances. Now it's time to build our mathematical protractor to measure angles. Thanks to a fundamental rule called the Cauchy-Schwarz inequality, our inner product engine guarantees that the similarity between two vectors falls within a strict mathematical boundary. It essentially traps the similarity score, kind of like how cosine similarity is always bound between -1 and 1. By trapping this value, we can extract a really clean, understandable angle. Notice the red angle marked omega here. This angle tells us exactly how aligned the orientations of our two vectors are, totally regardless of how long the vectors actually are in space.
Which brings us to a massive, absolutely crucial concept, orthogonality. This is just the formal mathematical term for vectors that are perfectly perpendicular to each other. When the angle between two vectors is exactly 90 degrees, their inner product evaluates to exactly 0. And in the high-dimensional language of machine learning, that is a huge deal. An inner product of 0 means these two pieces of data share absolutely 0 similarity in their orientation. Finding orthogonal vectors means we are finding completely independent, non-overlapping features in our dataset.
But wait, check out this mathematical quirk. Remember how changing the inner product changed the length of a vector earlier? Well, it changes angles too. If we change our inner product engine, two vectors that were perfectly orthogonal at 90 degrees under the dot product might suddenly shift to an angle of 109.5 degrees. The implications there are pretty staggering. By simply tweaking how the algorithm defines similarity, you can force it to see two previously unrelated orthogonal things as suddenly highly correlated. You're completely warping the shape of the space those data points live in, without altering a single number in the original dataset. Wild, right?
And that brings us to our final section, Part 5, the power of projections.
So, why do we even care about projections? Well, because real-world machine learning data is massive. We're often dealing with thousands, maybe millions of dimensions. Think of a high-resolution image where every single pixel represents a completely different dimension. That is way too much data for efficient processing. Projections act as a solution here. They allow us to compress that high-dimensional data down onto lower-dimensional feature spaces. We do this to extract the most important, fundamental patterns in the data while making sure we minimize the loss of any useful information.
Think of an orthogonal projection literally like shining a flashlight straight down from above and casting a shadow of our data vector onto a much simpler surface, like a one-dimensional line. Take a look at the visual here, casting that exact perpendicular shadow. The spot where that shadow hits the line at a perfect 90-degree angle, that's our orthogonal projection. It is the absolute closest possible approximation of our complex, high-dimensional vector that can possibly exist on that simple line.
Now, to actually compute this shadow without getting bogged down in dense mathematical notation, we can break the algebra into a totally digestible three-step procedure. First, we find the coordinates, basically asking how far along the line does the shadow actually fall. Second, we find the exact projection point itself in space. And third, we construct the symmetric projection matrix. Think of this matrix as the actual code the computer's going to use. It acts as a mathematical machine. You feed it any high-dimensional vector, and it instantly crushes it down into the perfectly correct shadow on your line.
And we don't have to stop at a 1D line. Let's see how this builds when we project onto a flat 2D plane instead. The logic remains exactly the same. We're just casting a shadow onto a slightly more complex surface. A subspace we'll call U. Why a 2D plane instead of a line? Well, a 1D line might only capture, say, the overall brightness of an image dataset. But a 2D plane? That can capture both brightness and texture, preserving much more of the original story. By doing this, we give our machine learning algorithms a perfectly simplified, yet highly informative summary of the original dataset to learn from.
Take a look at this quote right here. The optimal linear projection is an orthogonal projection. As the source material definitively states, an orthogonal projection isn't just one of many choices. It's mathematically the best possible linear mapping for data compression. When we project data perfectly perpendicularly, we guarantee that the compressed representation is as mathematically close to the original data as possible. This geometric foundation is the exact engine driving incredibly powerful real-world algorithms like principal component analysis, or PCA.
So, we've seen how analytic geometry acts as a translator, turning our complex world into a language that algorithms can actually process. It gives us our lengths, our angles, our distances, but it leaves us with this final, genuinely fascinating thought. If swapping a single mathematical engine, the inner product, can completely redefine angles, lengths, and the very shape of space itself, what hidden secrets and unseen patterns in our massive datasets are simply waiting for the right geometry to unlock them? Something to think about.